what have we covered so far? We said that we have standard cell libraries. We've gone through details of standard cell libraries. We've looked at all the different information that's necessary for every standard cell in order to be able to design circuits with the standard cell in a library. We saw that there are different varieties of library may be available with different cell heights. And important to notice that standard cell heights are in a library, all standard cells will have the same height. Okay, so with that background, let's go over the backend flow. So what you see here is an input to the backend flow is the behavioral Verilog and the timing constraints. So that's 1 and 2 here. So you start with the behavioral Verilog code, timing constraints, and these are provided as input to synthesis. Synthesis is software that will take behavioral Verilog and convert it to a gate level netlist or to a logic circuit. So the output marked as 3 here is the logic circuit in Verilog format, also called a gate level netlist. And then the timing constraints that are provided to synthesis. Timing, by the way, timing constraints are nothing but clock definitions and any other timing characteristics of a circuit. Those are needed to run synthesis, and whatever timing constraints or timing definitions are provided as input, they will also be put out as output by the synthesis. So 4 and 2 are more or less the same thing. Only the style of the SDC of the timing constraint may change. The timing constraints themselves are in a format called SDC. So one of the things I want to show you in this slide, I want to convey in this slide, are the different formats that are used to convey design information. What I have talked about so far is the formats that are used for conveying the technology information. Standard cell libraries constitute the technology that you're going to use for implementing a circuit. The circuit itself, the design itself, is described with various formats. Various aspects of the design are described or captured in various standard file formats, and I want to introduce those formats to you in this slide. So the inputs to synthesis are Verilog format, and the timing requirements, which is in SDC format, where SDC stands for Synopsys Design Constraints. Okay, it's a format that was created by the company Synopsys, but now it has become a standard. So you have behavioral Verilog and SDC coming into synthesis. You have gate level netlist in Verilog format and SDC coming out of synthesis. And then the output of synthesis goes into place and route, which is the automatic layout flow. So in place and route, we are creating the layout of the circuit through automation tools. Place and route itself comprises broadly 3 steps, and these 3 steps are called placement, clock distribution, and routing. The first step is placement. So the placement piece of place and route has 3 inputs primarily. It has the gate level netlist or the logic circuit is one input. The timing requirements, also called timing constraints, is the other input. So that's 3 and 4. But you also need to give it a floor plan as an input. The floor plan indicates the size and the shape of the block within which the circuit will be implemented. So if I can illustrate that, let me try to illustrate that with a. So I'm going to illustrate floor plan. So first of all, let's do this. You have standard cell. Let me see if I can make this a little bit better. Okay. Let's say I have a standard cell library comprising bunches of standard cells, and I'm going to call these standard cells. They all have the same height. So these are all the different standard cells in the library, okay, and different widths at the same height. So my drawing is not great, but all these heights are just imagine that these are all the same height, h, okay. And remember, there is h is described in terms of number of tracks. So in a standard cell library, you'll have maybe, let's say 1,000 cells or whatever number of cells there may be in the library. I'm just saying 1,000. Now the netlist will have instances of these 1,000 cells. And then the cells will have to be placed. To start the layout process, you need to place the cells. But in what area do you place the cells? And what are the constraints on that area? That is described in the floor plan. So the floor plan physically, oops, let me see the cursor here. Okay, so these standard cells have to be placed in order to start the layout process, and then to do that, we need to first create a floor plan. In a floor plan, you will indicate the dimensions of the area or the block in which you're going to do the placement. So let's say that my block is going to be rectangular. It doesn't have to be rectangular. You could even do the placement in some kind of a rectangular or a rectilinear shape. Oops. This is called rectilinear shape. And pardon my wavy lines, but just you have to imagine that these are all straight lines. And this is a rectangular shape. So let's say that we are a rectangular shape. In this rectangular shape, the standard cell rows will be there. So these are all the standard cell rows, let's say. And so these are all to be this will be all defined in the floor plan. So you'll have the width and the height of the block itself, or the area in which the placement happens, and then the standard cell rows. And since all the standard cells are the same height, they can be neatly arranged in rows. So now let's say that here the standard cells will be placed. Okay. So you may have like whatever millions of standard cells are there, they'll all be placed in these rows. In between the standard cells, you may have some gaps. At the end of the placement, those gaps will be filled with what are called filler cells, which are also part of the standard cell library. So if there's any gap there will be like a filler cell placed in there, which is in the library. Now the floor plan, the floor plan information comprises this width, the height, and all the standard cell rows. For example, you may decide for some reason that you don't want any standard cells to be placed here. So you may not keep any rows in that area. You may want that space to, for example, house some analog circuit or something else that you may need to include in the layout. But so the actual details of the standard cell rows will be in the floor plan. And the other very important thing the floor plan will have is where the ports are located. So your input ports and output ports, where are they? Along, and usually they'll be along the edge of the floor plan. So this is where all the different input ports and output ports are, let's say. So that information will also be in the floor plan. So this is going back to the slide now. So this item number 5 here is the floor plan. Okay. Now the floor plan itself, in what format do you provide that information? The floor plan information can either be in the form of just tickle scripts that the placement tool will read and execute and just basically build out the floor plan before it's starting to place the standard cells, or it may be in a special format called DEF. So the LEF format which we were introduced to earlier was the library exchange format. DEF stands for design exchange format. So this is a format for describing a design, not a library. Okay, again, library constitutes the technology that we use for implementing a design, and it has its own formats. The design is the design, and that has its own formats as well. One of the formats that describes the design is actually the netlist format, which is Verilog. The timing constraints are design specific. They describe what the timing requirements of the design. Those are in STC format. And then the physical information of the design, the kind of layout related information of the design, is in the DEF format. That's the design exchange format. Okay. And so there are 3 primary inputs for placement: the Verilog netlist, the timing constraints in SDC format, and the floor plan. With that information, a placement tool, which is a kind of electronic design automation or EDA tool, a placement tool will place the standard cells in some optimal manner. And the algorithms that are used for placement are very advanced algorithms. And these tools are even very advanced right now, in the sense that they can take a netlist containing 2-3 million cells and place them in some optimal format. It's not going to place them in an arbitrary manner. It's going to place them in a very optimal manner. What is the meaning of optimal? Well, optimal means two things. One, the total length of nets has to be minimum. So the placement algorithms will place the cells in such a manner that when you actually connect the nets, the length of the wires added up, sum total of the length of all the wires should be minimum. So that's one cost function that the placement tool optimizes. The second thing the placement tool does is that it is aware of the timing that is needed. And so if there are certain cells that are connected to each other through which a signal will flow, and the need for that signal to flow through the cells is, if there's a requirement that the signal goes through very fast through a set of standard cells, then those standard cells will be placed nearer to each other. And if there are other standard cells through which a signal can take longer time to go through, then those cells can be placed further from each other. So those that kind of timing awareness is also built into the placement algorithm. So the placement algorithm will create a placement or an arrangement of standard cells in rows such that the sum total of all net lengths is minimized and timing is optimized. Once the placement is completed, then we know the locations of all the flip-flops in the design. And the flip-flops need a clock. So during placement, the clock is just an ideal clock. There is no the clock is not physically implemented during placement. The only thing that happens during placement is the standard cells are placed. Once the standard cells are placed, the locations of all the flip-flops is known. And once you know the locations of the flip-flops, one can implement the clock. One can distribute the clock, because every flip-flop needs a clock. And so the clock distribution is the next step after placement, where the clock is physically implemented. And you can think of it as a kind of a tree. The clock enters the design through one port in the floor plan, an input port. And from that port, it gets distributed to all the flip-flops and the sort of the topology of the distribution. You can think of it like a tree. And the clock has the clock tree has all these branches that go to all the flip-flops that are spread all over the floor plan. And as the clock is being distributed to the flip-flops, it will be buffered. So the buffers will be used in order to keep the signal quality of the clock good. So that is the clock distribution step. And once that is done, then everything is ready in order to implement the nets, physically implement the nets, which is the routing step. So in routing step, you're actually routing the nets. You're connecting all the standard cells that need to be connected. And that routing step will use the different metal layers that are available. How does the router know what metal layers are available? Because you will have provided the technology left to the place and route tool. And so the router will read the tech left and knows, okay, I got 8 layers of metal available. Metal 1 has to run horizontally, metal 2 has to run vertically, metal 3 has to run horizontally, and so on. It knows that information from the tech left. It knows what the minimum width and spacing of the metal layers is. It knows what the pitches are. And so using that information, it will then complete the routing.